Hello guys, I'm Juan Pablo Garcia. I'm part of the Statics Endgame team, and this is our Eggstronaut project. Our team members are So Huerta, Naila Gomez, me, and other two guys that forgot to upload their photos. But their contribute definitely a lot. It's Rodrigo Sanchez and Diego Salazar. So going on. Our main objective was to create a moonlander that would withstand a 1 meter drop with the egg, the extra intact. So we wanted to design cell structure, and the design requirements or our limitations were that it should withstand a 1 meter drop minimum. It had to weigh less than 450 grams. It had to measure less than 300 times 300 millimeters. We could only add glue at the joints, not along the members, and we could not paint the lander. During brainstorming, we based our designs on many Moon and Mars landers that already exist, but we saw in a video uh, like a piñata or a star shape structure with an egg inside with then a 2 stories drop with the egg still intact. So we added some concepts of that design, some ideas, and we use an hexagonal shape since from what we read, honeycomb design was used on cars to disperse the force during an impact and protect the driver. So we wanted to use that shape for that same purpose. And going on, these are our initial designs. The middle one is our last design, but the other shapes were some initial concepts we came up. Our prototype design, this is our prototype with a width of 7.75 inches, a height of 4.5 inches. The egg holder is a lot smaller in order to maintain the egg on the same position without moving even an inch. So it's 3 inches width and a 1.5 inches height. It failed. It failed horribly. We needed to improve the design, and so our improvements were to add a leg, just one leg based on the piñata design. The honeycomb design stayed. We saw that as really successful and as really good, and we added like a cage on the upper side of the egg holder so the egg wouldn't move out at all. Then we did some software testing on the leg. This is our a rough design of the leg with 6 members, and we calculated at 2.387 pound, well, Newton. This is in pounds, I don't know why, but it was newtons. 2.387 newtons force of impact, and the forces along the members we found out that they were distributed pretty evenly, so we count it as a success since there are pretty small forces and is and are pretty evenly distributed. So as you see on member 1 and 2, it's a zero point 0.5 Newton compression force, and from members 3 to 6 is a zero point 0.8 Newton compression force. We use an online free software to calculate this. It's pretty easy to use, uh, pretty intuitive. Then we did our hand calculations. Well, some of them. As you see, we used a parachute on our design, on our final design, and it helped a lot since it reduced the velocity to 6.15 meters over second, which in turn reduced a lot the force of impact to 2.387 newtons. And these are the things below the force of impact are the nodes and the members. There's listed the length of the members and the coordinates we use to calculate. So this is our problem, the free body diagram, the knowns and unknowns, the equilibrium equations. So since pretty much the sum of the forces on the x-axis and the y-axis were cancelled, and the result was going to be 0 is equal to 0. It wasn't pretty. It wasn't useful at all for the analysis. So we just used the sum of the forces on the z-axis, and I tried to use some of the moments according to A on the y-axis. Some of the moments according to A on the y-axis, but that wasn't helpful at all because I didn't knew how to approach this problem since we had 6 variables, and from the software we assumed that the member OA and OB were going to be equal since their length and directions are pretty much equal, as the same from OC, OD, OE, and OF. That was the only way that we could approach solving this problem, and we weren't successful. As you see on the bottom right of the right picture, we got that force on the OC members, which in turn are the forces on the OD, OE, and OF members were equal to 0, while the forces on the OA member, which in turn are the forces on the OB member, were equal to 2.45 newtons. So that doesn't make any sense at all. So I went with the software forces, which are 0.8 newtons in compression and 0.5 newtons compression, and that's what we went for. But yeah, just to clarify that we didn't knew how to approach this problem since there were too many variables, and 2 of our equations weren't useful. So yeah, going on, this is our final design. You can see the egg and the parachute, and you can see the leg we added. So it's pretty much the same as the prototype. We just made the main frame, the base frame, the outward frame sturdier. We reinforced it. We added a parachute and we added a leg, a single leg with a kind of cone shape. For the static analysis, we also calculated how the drag affected the velocity, and from that we calculated the force of impact. So these are the equations of the on the left side. So these are final design, and these are the final design measurements and specifications. It has a width of 7.75 inches, a height of 4.5 inches. As I said, we added the cone at the bottom. We maintained the hexagonal shape. We added a parachute and we made the main frame more sturdy. We reinforced it. Performance. It was a pretty good performance. It withstood a 1 meter drop, just weighing with the egg 140 grams. So it was really light, and even though it just withstood a 1 meter drop, the lightness proved that our model was strong enough, really strong. And conclusions, our objective was achieved. Finally, the design withstood a 1 meter drop without the Eggstronaut breaking, and was successful. And these are the results. That's the 1 meter drop. The 2 meter drop. So thank you, and that was our project.